Hi everyone. In this session, we'll discuss two important concepts in thermodynamics, namely the thermodynamic coordinates and the thermodynamic equilibria. Before discussing the thermodynamic coordinates, let us introduce the concept of state of a system. You know, in mechanics, in order to specify the state of a system, we are using parameters like position, momentum, energy, etc. The state of a system represents the totality of macroscopic properties associated with a system. Hence, in order to describe the thermodynamic state of a system, we will be using a number of variables or parameters which are also known as thermodynamic coordinates. Hence, thermodynamic coordinates can be described as those quantities which defines the macroscopic state of a system. By macroscopic state, we mean the state of a system as a whole, or those properties which are regarded as the average property of the system. The examples of thermodynamic variables or coordinates are the pressure, the temperature, the volume, the composition or mass, etc. Hence, if we know the thermodynamic coordinates like pressure, volume, temperature, etc., you will be able to make a complete description of the system. There are many other thermodynamic coordinates that we will come across in the coming sessions. Now, to begin with the thermodynamics of systems, we consider a system what is known as a simple system. So what is meant by a simple system? Any system which can be described by minimum number of variables such as pressure, volume, temperature, etc. can be regarded as a simple system. So the simplest of the thermodynamic system consists of a fixed mass. So it consists of a fixed mass of an isotropic fluid. What is meant by isotropic fluid? A fluid means either liquid or gas, whose properties remain the same in any directions or everywhere inside the system. That is known as an isotropic fluid. So a simple system consists of a fixed mass of an isotropic fluid, and it is not influenced by external fields. Like you say gravitational field or electric field, magnetic field, etc. So these fields do not have any influence on the properties of this system, and such systems can be described using the three measurable coordinates. So they can be described using measurable coordinates such as pressure, volume, temperature. Hence, such systems are also known as PVT systems, pressure, volume, temperature systems. They are also known as PVT systems. The best example is that you take a container which is filled with, you say, gas. A container, you are having a container of any arbitrary shape and it's filled with some sort of a gas. So these are the gas molecules, and these gas molecules are uniformly distributed inside the system. You know that depending on the composition of the gas or nature of the gas will be exerting certain amount of pressure. So I can say that it will be having a pressure. You know, the pressure is nothing but due to the average force that is exerted on the walls of the container due to molecular collisions. Then the gas will be having a particular value of temperature, and certainly this gas is having a volume which is nothing but the volume of the container. So such a simple system can be regarded as a PVT system. Now coming to the case of thermodynamic coordinates, all those coordinates, so thermodynamic coordinates are defined as the properties thermodynamic coordinates these are the properties or quantities that describes the macroscopic state means thermodynamic state of a system. So that can be the definition of thermodynamic coordinates. Examples already we have seen. Now, having defined what is meant by thermodynamic coordinates, we are in a position to define thermodynamic equilibrium. So in order to define thermodynamic equilibrium, we should first understand what is the meaning of equilibrium, or why we are bothered about studying systems which have attained equilibrium. So we can say that an equilibrium state or equilibrium is a simple condition. I can say it's a simple or simplest condition. Simple condition of a system. And what is speciality of such a condition? In this condition, the system will be exhibiting a set of, in this condition, system exhibits or shows a set of identifiable and reproducible properties which can be can be measured accurately, or you can say precisely. So this is why it is okay, a much sought after condition of the system. The system will be exhibiting a set of identifiable and reproducible properties which can be measured precisely. And we can say that the properties of the system will be independent of time. Why it can be measured precisely? Because properties or parameters of the system, properties of the system will be independent of time, So that is something very, very important. That is why we call it as equilibrium. So equilibrium is a condition where the properties of the system will become independent of time, and since they are independent of time, you can measure them precisely, and also you can reproduce the same properties later, at a later point of time. Now there are three major types of equilibria. So what are the types of equilibria? Types of equilibrium. There are three major types of equilibrium. The first thing I can say, it is a mechanical equilibrium. The second one is chemical equilibrium. And the third type of equilibrium is known as, what you are familiar already with, thermal equilibrium. Let me add it. Equilibrium. Now, what is the condition for mechanical equilibrium? The condition for mechanical equilibrium is that there should not be any unbalanced force. No unbalanced force. No unbalanced force anywhere in the system or between the system and the surroundings. And it can be represented by the mathematical condition that the pressure on both sides of the system and the surrounding should be equal. If we have got, you say that you are having a simple system, let this be our piston and cylinder. That is a common system that we usually discuss. This is my mobile piston, and some gas molecules are there inside the cylinder. Okay, and you know that the weight of this, suppose that you are putting some weight over the piston, you say some mg, including the weight of the piston, mg. So you know there will be just a weight mg acting down, and these gas molecules will be exerting a pressure in the upward direction. So there is a pressure exerted by the gas molecules upward. You say this is P1, and the pressure due to this weight of the these masses, that will be acting downward, P2. And the condition of mechanical equilibrium of the system is that this pressure exerted by gas output P1 should be equal to P2. And you know, when P1 equal to P2, the position of this piston will be remaining same. And I say there is there is no any unbalanced force here, so the system is in mechanical equilibrium. Now coming to the case of chemical equilibrium, whenever there is no net chemical reactions taking place inside the system, or no new products are formed, there is no any net movement of molecules or entities inside a system, we will say that the system is in chemical equilibrium. And the condition for chemical equilibrium can be represented by writing mu1 is equal to mu2. Maybe this symbol mu is a new term for you. Mu is known as chemical potential of the system. Chemical potential of the system. We will describe this term chemical potential in detail in the later modules. Remember, for the time being, chemical potential is a quantity or a physical quantity or a parameter which decides whether or not there be a movement of particles across a boundary or across between a system and the surrounding. It is very similar to the role of particle concentration or concentration gradient in the case of the process of osmosis. Now, when chemical potential on one side is equal to chemical potential on the other side, there won't be any more net transfer of particles from one system to the other and vice versa. So that's the meaning of chemical equilibrium. Now coming to the third one, which is known as thermal equilibrium. You know, thermal equilibrium is a state where there is no net heat transfer. No net, I'm using the word net everywhere, heat transfer between different parts of the system or between the system and the surrounding. And the condition for thermal equilibrium is already discussed by the zeroth law of thermodynamics precisely. That is, the temperature on both sides should be equal, or temperature of the system should be equal to the temperature of the surrounding. So these are the crucial conditions for the three different types of equilibria. You can regard one more type of equilibrium that is known as phase equilibrium. We may not be discussing much about phase equilibrium here, but remember, for the time being, mechanical, chemical and thermal equilibria are the three different types of equilibrium possessed by a thermodynamic system. Now our aim was to discuss and define what is meant by thermodynamic equilibrium. Whenever a system is showing or is in a state of combined state of mechanical, chemical as well as thermal equilibrium, we will say that the system is in thermodynamic equilibrium. So thermodynamic equilibrium is a state in which the system is in mechanical equilibrium, it is also in chemical equilibrium, and the system is also in thermal equilibrium. So the combined condition of all these three equilibria satisfied by a system is known as thermodynamic equilibrium. And we will see that most of the systems that we are going to discuss hereafter will be either in a state of thermodynamic equilibrium or they will be trying to achieve the state of thermodynamic equilibrium. We will discuss those processes in the coming sessions. Thank you.